Hello, I'm Moritz von Lotz. I'm presenting joint work with Pablo Gomez and Dario on using geodesy-ANNs on studying the asteroid Bennu and using them especially with Osiris-Rex data. So, in recent years we had many different missions to asteroids, some with landers, some with orbiters. This one, some of you probably recognize. This one even more. It was the iconic Rosetta mission. And this one is the most recent one, which will also be subject of this talk, the Osiris-Rex mission to the asteroid Bennu. And apart from these three, there were some others. So there was a Dawn mission to Sirius and Vesta, which used the ion drive to great effect, but didn't land. There was the Rosetta mission we mentioned, there was Near Showmaker, and Hayabusa 1 and also 2. And all of these have in common that they go to small bodies, which often have an inhomogeneous gravitational field. So even though they're too small to undergo internal differentiation, they still have density fluctuations, and often they're not even spherical, because the gravitational pull wasn't strong enough yet to pull them into spherical shape. So this is of course challenging for orbit planning, especially if you want to go very close. But the density heterogeneity can also be very insightful, because as you see here on the right, and asteroid Itokawa, there it was found that this head, here called in red, had a much higher density than the rest of the asteroid. So even almost twice as much. And the explanation is then that Itokawa must have been formed by a collision of two different bodies of different densities, which then stuck together. And this holds for many bodies, where knowing something about the internal mass can help you understand something about them and their history. So there have been several models to model the inhomogeneous gravitational fields. So if you assume a uniform density, then you can use polyhedral models, which then use a shape model to really uniformly integrate over its interior and give a gravitational field. Alternative are spherical harmonics, where the difference to a uniform sphere is modeled. And it works very well, and the problem is that there are convergence issues below the boundary sphere of the object. And especially with very irregular objects, this can cover a significant area of possible orbits, which are physically possible but not calculatable with spherical harmonics. So in a previous work, we presented GeodesyNETs, which are a neural network architecture to directly learn the mass density field of a small body. And they have a sinus activation function, so are very similar to the Siren network that are already used. And we tested them on synthetic data, and the result was that it was a fit within 1% error on synthetic data of Bennu, Itokawa, and Churium of Geremenko. And this 1% error was achieved close to the surface, so where any error would be most pronounced. But this was synthetic data, and now our current work is to apply these geodesyNETs to real flight data from the Osiris-Rex mission to the asteroid Bennu. And since we don't have a ground truth of its mass density fields, we propagate orbits as a method of validation based on the learned mass distribution. So geodesyNETs are, network architecture to learn the density, and you can see here on the right the basic structure of it. So the network has 3 input neurons, one for each part of a Cartesian coordinate, then some dense layers, which are densely connected, and then one output neuron, which gives out the estimated density at these coordinates. So you put in a Cartesian coordinate, the 3 components to the networks, let it filter through, and at the end you get the predicted density. And once you have this, well, you can call the network at different points within your body, and then you get a density model. And by doing this, you can integrate overall this model points, and then you get a gravity field for the surroundings and specific predictions of gravitational acceleration for observation points in the vicinity of the object. And if now you have real measurements of the gravitational acceleration at these points, you have of course a difference. This forms an error, and then you can backpropagate this error to the network to train it to reduce the error. And this, after suitable learning, will then result in a network that predicts a density model which is consistent with your potential or acceleration measurements of the gravitational field. Of course, since the gravitational inversion problem is underspecified, this will be one of several possible density models, which are consistent with observations. And now in this general case I've described, there's no shape model needed. But if there's one available, we can train the differences to uniform density. So here we assume the differential case, where we have the shape model given in some polyhedral form, and then we put mass concentrations in it to model mass distribution with uniform density. And then we train the network to learn the differences, and this can help in discovering density heterogeneities. And at least with synthetic data, there's also a higher accuracy of the resulting orbits, because more information was given in to propagate them. So these are the loss functions used for the 2 different cases. So here we see y are the observations. So we iterate through the observed points outside of the body in question. And y are the predictions, y hat are the observations. And we see here that there's an additional parameter kappa. And this is because we found that it is easier to predict relative densities instead of absolute ones. So each position in the network predicts a density of how much the density at this point is relative to the overall density. So the network doesn't have to predict the total mass of the asteroid. And this is then one thing where we use kappa as a scaling factor to, at the end of the training process, put that to a proper value to fit the gravitational measurements. And now with the differential case, you see here that there's this additional parameter ym, and this is acceleration measured from the Mascon model, which assumes uniform density. So here the loss function is really the difference between the prediction and minus the Mascon model minus the observations. So that if the observations would fit uniform density, then we would here train a network which predicts 0 at each point. So moving on to the target of our analysis. So Bennu is a near-Earth asteroid in the Apollo group. It orbits the Sun at distances between 0.9 and 1.35 astronomical units. And this means that it crosses the Earth's orbit. There is very, very small risk that it might at some point impact Earth. There's a diameter of 484 meters, plus minus 10. the mass around 7.3 times 10 to the 10 kilograms. And it rotates around its axis at roughly every 4 hours. And the picture you see here on the right is already aligned with the rotational axis. That you have the equator in the middle and then an axis going from top to bottom. And this asteroid was visited by the Osiris-Rex mission from December 2018 to March 2021. And the main purpose of the mission was to acquire some material of Bennu and then bring it back to Earth. So the return trip is still on the way. But during this mission, the Osiris-Rex spacecraft found that Bennu occasionally emits small pebble-sized rocks. So these are probably from thermal fracturing, because they appear on areas which are heated by the sun. And since they are very close to Bennu, much closer than Osiris-Rex was, they experience much higher differential gravity influence. So they're very helpful in mapping the gravitational field. And here we used pebble orbits, which were cataloged and modeled by GeodesyNETs in their paper from last October called Heterogeneous Mass Distribution of the Wobble Pile Asteroid Bennu. Now, if we look at some of these pebbles, I'll call them pebbles from now on, we see they have very different trajectories. So some of them just get emitted from Bennu and then do maybe one orbit and then impact again. Some have multiple orbits before re-impacting, some escape. And here we have some measurements of maybe pebbles that were not tracked in their initial emission, or that even came from the surroundings, who just approach, interact, and then fly away again. So the top row shows these pebble trajectories in inertial frame, and the bottom row shows the same in the co-rotating frame of Bennu. We've noticed that Bennu rotates every 4.3 hours. And this is quite helpful for us, because now the same trajectories have experienced many more different sides of Bennu, and thus allow more influences about its gravitational field. So the colors show the difference to a uniform model. So for each position in the pebble's trajectory, we calculated which gravitational acceleration it would experience if Bennu had a uniform mass density, and then colored the deviation from that here in red. So the dark blue ones are those which perfectly align with the uniform density model, and the red points are those that deviate. Now, this deviation doesn't have to mean it's only density heterogeneity. It can also be unmodeled forces, and we're coming to that shortly. So in preparing this dataset, we took the 313 pebbles that were modeled by GeodesyNETs. There are probably many more which orbit Bennu, but which were not tracked in sufficient detail that a trajectory could be recovered from them. And from these that were recovered and are in Spice kernel released by GeodesyNETs and the Osiris-Rex mission, there we sample the positions and accelerations every 5 minutes. We sample the accelerations by numerical differencing from the velocity values. And then we obtain about 350,000 samples. And now from these, we have several other forces which influence the trajectories and are not only gravitational forces. So we calculate the solar radiation pressure at each point and subtract it, except of course if they are in eclipse. And finally, to put them into a proper scale for neural network training, we use custom length and time units. So the length unit is so that it becomes a scale around 1. And the time and acceleration units are chosen such that the total mass of Bennu in these units will be 1. And that makes training and scaling easier. Now, the differences to synthetic data are, of course, several non-gravity forces. So we mentioned solar radiation pressure. But there's also infrared radiation from Bennu, or there's reflected solar radiation from Bennu, or other maybe tidal forces, which we don't model in detail because we want to see what can be done with a relatively simple machine learning model. Of course, there's also measurement noise in the pebble positions, and there we will see what kind of impact this has on our return. And finally, we see that in the synthetic dataset, we had fine control over where we sample to get the maximum amount of insight over this gravitational field. And here, of course, we just observe some trajectories, and these will be what we have. So we have no control over the sampling positions. So some results. Now, these are visualizations of the densities learned by the neural networks. And we see here the non-differential case is just trying to predict absolutely the mass density. And here the 3 color-coded pictures are then cuts through the 3D prediction of the density. And we see here 2 things. First, well, that there are some artifacts from the network training, but also that very roughly the shape of Bennu is recovered with this equatorial bulge without having used any shape models. And for the differential training, we see that mostly the scale is much lower. So if you look at the color coding scale, it's a factor of 20 less than the absolute one. And this means here that the differential approach, in contrast to synthetic data, didn't find any meaningful density variations within Bennu. So we assume that this is because the measurement noise was much larger than the density fluctuations you could find there. So this is why this basically random network noise overshadows the faint signal of the different densities. And the network noise is, of course, a result of this measurement noise, mostly that. So we saw these densities, but again, we don't have a ground truth density estimation of Bennu. So to validate our approach, we use the predicted gravity field from the predicted densities and propagate orbits of some pebbles. And for that, we use the 120 pebbles with the longest duration, so from 1 day to 14 days. And we remove them from the training set used to infer the mass density, and then train the networks without these. And then on each of these holdout pebbles, which are not in the training set, we select an early point on the trajectories and then propagate based on the predicted gravity acceleration. And of course, we add solar radiation pressure. And a result was that when we average over all the 120 holdout pebbles, we get a propagation error in the non-differential model of about 40 meters after 3 hours, which is very similar to the error of a Mascon model, meaning assuming uniform densities. But now our approach here with the non-differential model got similar results, but without requiring a shape model. And we also saw the densities, but also in the validation, that the differential approach doesn't yield an additional benefit yet, because the signal there is very faint. So if we see how this looks at plots, here we compare the orbit propagation error from the GeodesyNet, from a Muscal model assuming uniform density, and as a comparison by assuming a point mass model of Bennu. And here we see that the errors of GeodesyNets and Muscal models are very similar. So for the non-differential case, GeodesyNets has this very slightly higher error. For the differential case, very slightly lower. But they're both much better than assuming point mass. So these time steps here are of 10 seconds each, and so they're about 3 hours. And they're also much finer than the 5 minute intervals we use to sample to generate our data. So it makes sure that it's not only learning these samples at 5 minute intervals. So to sum up, we applied the geodesyNETs to real flight data from the Osiris-Rex mission and evaluated this simple machine learning model, no modeling of non-gravity forces except the solar radiation pressure, and used it to directly learn the mass density function of the asteroid Bennu, and then validate this by propagating orbits. And on the result is we recovered very roughly the shape of Bennu, and the orbit propagation error is comparable to the use of a Muscal model, but without requiring a shape model. And future work is, of course, to focus on the differential case and to see which other non-gravity forces might need to be modeled to gain more accuracy there. Thank you.